Hello and welcome. Humanity has always looked beyond the horizon, pushing into realms far more extreme than anything on Earth's surface. Think about the vacuum of space, bombarded by radiation, or the crushing, corrosive darkness of the deep ocean. How do we even begin to explore these frontiers? The answer lies in the materials we use. Advanced materials science is the unsung hero, providing the literal building blocks for the probes, vehicles, and habitats that brave these hostile environments. Let's first consider what extreme really means. Outer space isn't just empty. Materials there face a harsh vacuum, which can cause them to release gases and degrade. Temperatures swing wildly, hundreds of degrees between sunlight and shadow. Intense radiation from cosmic rays and the sun damages plastics and electronics. In low Earth orbit, highly reactive atomic oxygen actually erodes materials. And then there's the constant threat of tiny, high-velocity micrometeoroids and space debris. Down in the deep oceans, the challenges are different, but no less daunting. Pressure mounts relentlessly, reaching thousands of times the atmospheric pressure at the surface in the deepest trenches. Saltwater is incredibly corrosive, a problem compounded by dissolved gases. Temperatures often hover near freezing, making materials brittle. And unique spots like hydrothermal vents add intense heat and aggressive chemicals to the mix. So, what do we need from materials to survive all this? First, a high strength-to-weight ratio is critical. Lighter spacecraft are cheaper to launch, and lighter submersibles are more buoyant. Materials must possess thermal stability to handle extreme temperatures and insulate vital systems. They need resistance to radiation in space and corrosion in the sea. They absolutely must tolerate immense pressure without buckling. They also need toughness to resist fractures and impacts, whether from space dust or undersea collisions. Ideally, some materials might even have self-healing capabilities for minor damage. Science is rising to meet these demands. We see advanced metals like titanium alloys, prized for their strength, low weight, and corrosion resistance, used in both spacecraft and submersibles. Super alloys handle the intense heat inside rocket engines. Ceramics offer incredible heat resistance, vital for atmospheric re-entry shields. And composite materials, like carbon fiber reinforced polymers, are superstars in aerospace, offering amazing stiffness and strength at a fraction of the weight of metals. High-performance polymers resist heat, chemicals, and radiation, used for seals, insulation, and more. Special syntactic foams, essentially polymers filled with tiny hollow spheres, provide buoyancy for deep-sea vehicles. Even how we design and build is changing. Additive manufacturing, or 3D printing, allows for incredibly complex shapes tailored to specific stresses, sometimes even combining different material properties within a single part. Powerful computer simulations help predict how materials will behave, speeding up design and reducing costly physical tests. Of course, challenges remain. These advanced materials are expensive to develop and produce. Recreating the combined complex harshness of space or the deep sea in a lab for testing is incredibly difficult. And ensuring these materials remain reliable for decades is a major hurdle. Yet, despite these challenges, materials science continues to pave the way. By understanding the brutal demands of these final frontiers and developing the innovative materials needed to withstand them, we are equipping ourselves to explore further and deeper than ever before. Thanks for listening.